Hello, and thank you for joining me in this presentation. My name is Marcel Padilla, and it is my pleasure to present to you our work on filament-based plasma. This work was enabled through the wonderful collaboration with Oliver Groß, Felix Knöppel, Albert Schörn, Ulrich Pinkal, and Peter Schroeder. We begin our journey by looking directly into the sun, the shining star of today's show that you have probably seen before. Its brightness makes it very difficult to spot any finer detail, so let's dim it a little first to see more. This is our sun during a solar eclipse. Now it becomes apparent that the solar atmosphere, known as the solar corona, has a crazy amount of structure in it that was concealed before by the extremely bright core. And this is our sun as seen by the NASA Solar Dynamics Observatory. Now we can see a lot of plasma filaments. These are the striking features of the solar corona that we would like to understand and model in this work. A closer look reveals the fibrous nature of these filaments. It is thus natural to want to find a description that relates to this structure. Thus, we depart on a mission to derive a Lagrangian plasma filament model that we can then use to create images like these. From solar physics, we know that these plasma filaments align with the magnetic field. Furthermore, this magnetic field is static, meaning that it's pretty stable over time. This means that we need to solve for a static magnetic field B to align our plasma filaments to. This static field can be expressed as an equilibrium of Lorentz force, gas pressure, and gravity, joined together by the magnetohydrostatic equation displayed here. This is the core equation we are trying to solve. Since this is an astronomically complex problem, we need to specify further model details we are going to use to approach a solution. So the time has come for some solar physics background. The strong magnetic field originates from the internal processes in the sun, which create magnetic filaments underneath the surface. These are bundles of strongly concentrated magnetic field. The buoyant nature of these filaments causes them to rise above the surface and expand. The expanded filament then exhibits a strong magnetic field with very little gas presence. Outside of this filament, we have the opposite situation, a weak magnetic field with much more gas. To simplify the problem, we take this observation to the limit. We decompose the entire space into a magnetic-only domain and a gas-only domain. This is known as the force-free current sheet model and will help us solve the magnetohydrostatic equation. So let's label the domain decomposition. M0 now has no magnetic field B and only gas, while MB only has the magnetic field B and no gas. The energy of the system can now be expressed as an integral of gas pressure and magnetic pressure on the flux domain MB. Our contribution now lies in the following theorem. A critical point of this energy solves the magnetohydrostatic equation. We refer to the paper for further details on this theorem. Thanks to the domain decomposition, we can now solve the MHS equation on the two domains separately. For the gas-only domain M0, the MHS equation collapses to the requirement of a hydrostatic pressure equilibrium. On the flux domain MB, once we know its shape and boundary flux on the sun's surface, we can solve for a Lorentz force-free field to fill the domain with. This is analytically always possible and legal given valid boundary conditions. We choose Neumann boundary conditions where we prescribe the normal flux on the sun's surface and demand zero flux at the interface between the gas domain and the flux domain. This model now allows us to update our mission, which has now shifted into finding the state MB of the flux domain that is a critical point of the energy according to the force-free current sheet model we just discussed. How can we handle this flux domain MB computationally? Our approach is to express MB using a filament-based description. Let's introduce this formally. So the objective is clear. We want to discretize the plasma into filaments because the footage reveals curve-like elements. The discretization of the problem through filaments is analogous to discretizing fluids through particles or vortex dynamics by filaments or rings, or muscles and hair by strands. We choose to represent the plasma state MB by a collection gamma of curves with thickness. Each one of these curves will be known as a filament, and these filaments do not overlap each other. The parameter of this discretization is the flux quantization per curve. It determines the size of each filament. Larger flux results in fewer, thicker filaments, while smaller flux results in more abundant, thinner filaments. Let's take another look at the energy of the system mentioned earlier. We discretize it by summing up the same energy expressed per filament. All we did here is computing an integral by first splitting the domain, computing the energy on the split domain parts, and then summing up the results. The pressure P is known from the hydrostatic pressure equilibrium, but how do we compute the magnitude of B? We can directly determine it from the filament collection gamma. Since the filaments are not allowed to overlap and cannot expand indefinitely due to the gas pressure, their thickness has to be constrained. Due to the preservation of the magnetic flux, we can then determine the magnetic field strength from the known flux and thickness. This computation also illustrates how the discrete energy depends on the spatial arrangement of the entire filament collection. Notice also the particular form of this integral. The filament description allows us to express this energy as a curve integral in the Euclidean metric. The way it is written, mathematically, it can also be interpreted as a length L in a non-Euclidean metric, which is spatially dependent on the terms inside of the integral. With this expression, we can simply write the discrete energy as the sum of length of the filaments with respect to the particular non-Euclidean metric, with the metric being dependent on the arrangement of the filaments gamma. You might now ask yourself, why? Why interpret this so geometrically? To answer this, let's remind ourselves that our target was to find a critical point of the magnetohydrostatic energy, which we now discretize as a sum of lengths. This means that our length interpretation now allows us to solve the problem using length shortening methods. This justifies the following conceptually simple algorithm. As the input, we have an initial set of filaments. On these filaments, we then compute the non-Euclidean metric. Knowing the metric, we then perform a curve shortening step, shortening the length in that particular metric. This will slightly move the filaments, and thus we have to recompute the non-Euclidean metric again. We repeat this process until convergence, where we have reached our desired critical point of the discrete energy. The resulting filaments then represent a valid solution of the magnetohydrostatic equation according to our model. Here is some footage of this process. An initial bundle of filaments comes with different magnetic field strength. What we see here is the iteration of the computation of the metric and the shortening of the curves. Shortening with respect to a non-Euclidean metric means that the shortest path won't necessarily be a straight line. You can think of it as if the space has been warped substantially. Here we also see that stronger magnetic fields expand further, as they are able to push more strongly against the exterior gas. This covers the main algorithm of our work. In practice, we need a good choice of initial filaments. So in our main target application, recreating the sun, we will explain how we initialize filaments for our algorithm. Luckily for us, NASA provides a large archive of solar magnetic surface flux data. The red bits here show where the magnetic field comes out of the surface, and the blue parts show where the field goes back inside. As you can see, the solar magnetic field is pretty wild. For our application, we now stipple the flux density into points of equal flux, such that the flux is approximately preserved locally. Areas of strong magnetic field have many stipples clumped together. So now the question is, what filaments do we feed into our algorithm? What shape should these filaments have, and how should they match red stipples with blue stipples? For the shape question, we propose to use the shape of ideal filaments. That is the shape a single filament would have if it wasn't limited by other filaments through the constraint that filaments do not overlap. We derive the exact parametrization and energy of ideal filaments in the paper. Mathematically, it is only dependent on the pressure distribution in the solar atmosphere. However, it is still not clear where to place these ideal filaments. How should the red dots be connected with the blue dots? Our approach here is to solve an optimal transport problem that minimizes the total sum of the energies of the ideal filaments in the initialization, meaning that we solve a discrete combinatorial problem that will tell us how to assign the stipples to each other. And this is how the initial filaments look like when we follow these instructions. We can then plug these filaments into our length shortening algorithm and receive our final filament collection that represents the plasma state MB that solves the magnetohydrostatic equation. How do we create neat images from this? By proposing a glow model that determines the brightness of the filaments. This includes plasma physics observations on the radiation of specific frequencies in the solar plasma. The total emission reaching the camera is integrated per pixel and colored according to NASA Solar Observatory conventions. Practically, this mimics the way an observatory would process the data. The choice of Lagrangian elements as filaments really comes in handy here, as it naturally recreates the fibrous details. For high-resolution images, we also subsample the filaments into smaller filaments. We refer to the paper for further details about our glow model. For the final image, we then slap on some surface details that we generated using basic noise mappings, and compare this to the real footage created from NASA observatory data. Of course, we are not limited by NASA data. We might as well design flux data or filament sets ourselves and run them through the code. We also add some animated noise to the glow to mimic the small-scale glow variation seen in real data. Here the same scene with a different view. And here we generated flux data through random noise and plugged it into our pipeline. So we stipple the surface, match the stipples, place the ideal filaments, minimize the energy of these filaments, and then apply our glow model. And since we are doing graphics, I bet you ask yourself the following. Can we blow stuff up? The answer is yes, we can. Sort of. This might sound confusing since we are solving for a static magnetic field. The magic word in graphics that enables explosion here is quasi-static viscosity evolution. What does that mean to us? That we can just twist the sun's surface during the energy minimization process. This adds energy to the system through the boundary and is akin to the energy added to the magnetic field through surface motion on the sun. To implement this in our algorithm, we simply add a step where we update the boundary points of our filaments. When now running the algorithm, the added twist causes the energy minimization to raise the filaments upwards, blasting them into outer space. In solar physics, this twist to solar flare mechanism has already been proposed, and it is neat that our algorithm shows this behavior too. Twisted magnetic field structures can indeed reduce their energy by expanding upwards. And with this last explosion, everything comes to an end. So let's have a quick summary of this work. We introduced a new physics-based approach to model solar plasma by filaments. The required solutions are reached by minimizing an energy, and we do this through a length shortening algorithm because we can interpret this energy as lengths of filaments in a non-Euclidean metric. Using quasi-static viscosity evolution, we created flare-like explosions by adding twists to the filaments. For rendering, we derived a glow model to turn filaments into solar-like images, and we have also given a complete pipeline to create solar-like images from flux data from any origin, which includes real-life data or data generated from artistic design. For the many details that could not make it into this talk, we encourage you to look at our paper. All code was implemented into Houdini and is available in the supplement material. Thank you for listening, and I wish you a sunny day.